All right, so go to this page, please. Close your laptops. Don't need them. Say, close your laptop. Jordan, close your laptop, please. Thank you, Mia, all the way. There you go. YouTube's going to hear this, so it's all good. All right, so go to this page. Tina, laptop, get your notes out. Oh, watch. All right. Normal distribution. Now, remember when we looked at box plots and histograms, we're looking at the skews. Yeah, you've got your three skews, your positive, your negative, and then you've got your approximately symmetrical. When it comes to this part of data on normal distribution, you're focusing on data that's normally going to be or has to be in a symmetrical or approximately symmetrical type of distribution. So it has to look like a mountain. And that's what we call a normal distribution, and it looks like a bell curve. You probably heard of before, a bell curve graph. Okay, all of that is going to be relevant. So normal distributions can have different centers and spreads, but always have that bell curve shape. So what that means is you can have data that's quite close like this, but it has to have a bell curve shape, or you can have data that's spread apart like this, but it has to have a bell curve shape. You can also have data that's higher up on the number line. As long as it has a bell curve shape, what you're looking for is making sure that it has that, that bell curve. Doesn't matter where it is, how wide or how thin, it's got to have a bell curve shape. Okay, that's what you're looking for when it comes to normal distribution. And we've talked about this before, standard deviation. So a normal distribution is completely determined by its mean and standard deviation. We haven't really covered standard deviation much before, okay, but we're going to look into it a little bit more now, okay? So this is a new thing. You probably haven't seen this before, but the 68, 95, 99.7 rule only applies, like I said, to bell curve shaped graphs, okay? And there's a simple rule connecting them, which is this. Okay? So whenever you see this, it's going to relate to these sorts of graphs now, okay? And they are essentially percentages. So you can kind of think of them as, remember when we looked at box plots, okay? Each section is split into 25% parts. Now, when it comes to histograms, you can sort of do the same, but using these values, we can split each section to certain specific percentages. Okay, and again, it only applies to your bell curve. So if you look at this data, it's a bell curve, great. One thing that I didn't mention here is what each of these values mean. So these little symbols, what do they all mean? This U is the mean. Okay, you can think of it as the center. When you look at a bell curve, the mean is where the main curve is, on the tip of it. Okay, and then these other symbols here, use another color. These little O's are your standard deviations. Okay, so when you're looking at a graph like this, what it's saying is, okay, you've got a bell curve. Okay, you've got your bell curve. The mean is in the middle. Okay, now when you're looking at your data, this is one standard deviation away from the mean. So this is what that means. One standard deviation. This is two standard deviations because it's the mean take away two deviations. And this is three standard deviations below the mean. If you go the other way, so if you have your mean right in the middle, if you move one spot away, it's one standard deviation above the mean. You move two spots away, it's two standard deviations. And in one more spot, it's three standard deviations. Now, the cool thing is the standard deviation splits it up, so you've got these percentages happening. And this is where we get the 68, 95, and 99.7 rule. 68% of your data is found, as you can see here, within one standard deviation away from the mean. So between this marker and this marker is 68% of your data, okay? And then to expand on that, 95% of your data is two standard deviations away from the mean. So you're focusing on all this data here. And that'll be 95% of your values. That's all in there. And then if you take it further again, three standard deviations away from the mean, okay, is going to be all of that data there. So 99.7% of your data. And then four standard deviations is going to be the rest here. Okay, so your standard deviations is kind of like on your number line, markers of where you can find how far your data is. So let's go into detail about that, and I'll show you why that all makes sense. Now, unfortunately, I should have drawn this in your notes, but I didn't. But I did. I'm putting this here because it does sort of help make sense of what we're doing. So one thing you can think of as well with your standard deviation, if you think about what that word means, deviation means how far away you are from something. So one standard deviation could be, depending on the values, would mean you could be above or below the mean. Let's say, for example, the average height here is like, I don't know, who's, let's say Kaya is like the average height here. I don't know if that's true though. So if I was to stand next to Kaya and like be this tall, I could be like, I don't know, 3 standard deviations away from her because she's the standard. But then if you compare her to say Rocco, who's like extremely tall, he could be like 5 standard deviations away from the norm, which is Kaya. Okay, that's how we understand. Oh, that's one way to sort of understand it. So how far are you from the middle? That's what a standard deviation is. So let's look at this. The risk circumference of a group of people is known to be normally distributed. So when you read that, that means it forms a bell curve shape with a mean of 17.7 and a standard deviation of 0.9. So that means one standard deviation away from the middle, the mean, is going to be 0.9. Now, the way that I would translate that onto this graph here, this is why I drew it here, is the middle is going to be 17.7. Oops. Right, the mean, right in the middle. And one standard deviation above or below is 0.9. So that means this next value here is going to be 16.8. 2 standard deviations away, so 2 from that here. So that would be 15.9. And then 3 standard deviations away, so over here would be 15. I'll write 15.0. Okay, so that's all the values on the lower end. How about we go on the upper end? So remember, one standard dev is 0.9. So that means above the mean, 0.9 would be 18.6. Okay, 2 standard deviations would be 19.5. 3 standard deviations above would be 20.4. Okay, so there are sort of your markers now of what you can use when you're making sense of the percentages. So 68% of your data would be between these two values. 95% of your data would be between those values. And then 99.7% of your data would be those values. So let's answer some of these questions. What range of the values could 68 of the percent of the data be between? So what range of your values are in the 68% market? So that would be these values here. So between 16.8 and 18.6. So actually, let's just go 16.8 to 18.6. Okay, so 68% of your data can be found in between those two. So between 16.8 and 18.6. Again, oops. It's helpful having these this around. It does help. I would actually suggest that you put something like this in your bound reference. Okay, it does help a lot. Question B, what range of the values could 47.5% of the data be between? So 47.5. Now, where do we get that now? Okay, so when it comes to working with this, you need to look at the percentages and add certain ones. So you're looking at where could 47.5% of your data lie? Well, let's get a calculator out and add some numbers. Okay, I could try and add all of these values and see what that might add up to. Okay, and if I did that, actually before I even do that, if you look at it, what am I adding up here? This half of the graph. What do you think, how much of that data would be, guys, if it's half of the graph? 50%. So I already know, well, you can't include all of this. Okay, so maybe I need to only include this. Okay, so let's add that 2.35 plus 13.5 plus 34. Okay, it's 49.85, so it's too much, okay? So maybe it's only this data here. So let's add that 13.5 plus 34% equals 47.5. So your data could lie between, based on those numbers, between 15.9 and 17.7. Or there's also another one. Where could the other ones be? What's the other range of data? Oops. Anyone know? Where would the other range of data be? Or 48%, or 47.5% of your data. Where could it be? I'm going to ask Tori, where do you think the other one is? So it could be between these values. Where could it also be? Good. So between 17.7 and 19.5. So, or okay, that's where it could be. The answer is where it could be, yeah? So just be mindful of what the questions say. Question C, what percentage of the values is between 15 and 16.8? Okay. So between 15 and 16.8, well, I'm looking at this data here. Okay, so 15 and 16.8, so that would be 2.35 plus 13.5, 15.85. So between 15 and 16.8 equals, what did I say? 15.85. Okay, so I'm looking at this data here. Question D, if there were 650 people in your group, how many are expected to have a wrist circumference of larger than 20.4? Round your answer to the nearest whole number. So larger or greater than 20.4 would be all the values above there. So it's 0.15. So for question E, it's going to be 0.15% of 650 people. Okay, so just put that in your calculator. 0.15 times 650 is 97.5. It does say to round, which equals 98 people. Okay, so that means 98 people are expected to have a circumference larger than 20.4, which is all the values above there. Okay, are there any questions? Okay, the main thing you need to remember with this is the middle is your mean. Okay, and then one standard deviation away from the mean represents each of these values. Okay, so that's one standard dev, that's two standard dev, three standard dev below, and if you go the other way, that's one standard dev up, two standard devs, and three standard devs up. Okay, and just be mindful of how the percentages are split so you can understand what you're focusing on depending on the question. All right, I think that is it.